So today we're going to be learning about number bases. So it's going to be more complex than the other topics we've gone through this week. So just make sure if you're confused at any time, you should ask your questions. You can unmute or type them in the chat, and I'll do my best to answer them. Okay, so starting off with yesterday's homework. How many zeros does 1948 factorial end in? Okay, if you solve this, you should go ahead and put your answer in the chat. Or if maybe you're a little bit confused, you can talk about how you think we should solve it, like what method we should use. That also works.
I have a question.
Yeah.
I don't know how to do the method to solve this problem.
That's fine. Well, do you know like what the method is, or is it just like you completely?
Yeah,
Yeah,
I'm pretty sure.
I don't know at all.
Okay.
I'm pretty sure you have to divide by 5 and 25.
Yeah. So the number of zeros at the end is determined by how many times you can divide the number by 10. And dividing by 10 is the same as looking for how many 2 times 5s there are. So basically, we're going to only look for the number of 5s because they are less common than 2s. And then the rule for finding the number of 5s was explained in the presentation. So first, you do x divided by 5 plus x divided by 5 squared plus x divided by 5 cubed, and so on until you can't do it anymore. So here you can see that you can see our math where we're rounding down. So 1948 divided by 5 rounded down equals 389, and so on until finally we just do 625, and we don't go any further because then the next power of 5 would be 3125, and that's bigger than our original factorial. So when we sum up all of our numbers, we get 484 trailing zeros, because that's how many 5s there are in the prime factorization of this number. Okay, find the greatest power of 2 that fits into 1829 factorial. So what's the strategy you guys think we should use when solving this problem? Does anyone have any guesses?
Do we do the same thing except like put bigger powers to 2?
Yeah, basically. You're correct. So basically we just replace 5 with 2, and then we just do all the powers of 2 that will fit in here. So the number of times a prime number a appears in the prime factorization of x factorial follows this general rule. You can see right there. So basically x here is 1829 and a is 2. So here's all of our math. And the highest exponent we're going to do is 2 to the 10th power, which is 1024, because after that it gets too big and it's not going to give us anything. So then after we solve all of that, you type it in your calculator, then you find the sum of everything, and it tells you that there are 1823 2's in the prime factorization of this factorial. So basically the answer is that, because that's how many that's the power it's raised to. Number 1, sure. So this was basically the same principle as the one we just did, except for 5 is now the number we're trying to find, and we're looking for, the question asked for how many zeros, but we're going to look for how many 5s because the number of zeros is like the number of 10s, and the number of 10s is basically the number of 2 times 5s, and we're going to look for 5s because they're less common than 2s. So we do the same rule basically, and then we find the sum of everything to get 484 trailing zeros at the end. Okay, what is the last digit in 1229 to the 899, the 8992nd power? Did anyone solve this? All right, that's fine. So anyone who knows, you can go ahead and say what strategy you would use to do this. Based off what we learned in the lesson, what's the first step?
Division?
Well, this question is asking you basically for what's the units digit. So do you remember from yesterday how we would find the units digit?
Oh, we would make a pattern.
Yeah, perfect. So we're going to list out the powers of 1,229 to find a pattern in the units digit. And the pattern is that basically it alternates between 9 and 1. Now we need to fit the exponent into that pattern. So remember, we could use modular arithmetic, but this is like a pretty simple pattern. So we know 800. So there's two numbers in our pattern, 9 and 1. And so if we do 8,992 mod 2, because there's two numbers in the pattern, then we get a remainder of 0. And that means that the last number in our pattern is the last digit.
1.
Yeah. So the answer here is 1. What is the sum of the last two digits in this number? So the strategy here would be not just to find the pattern for the last digit, but also the pattern for the tens place, right? So here's the pattern that you would find when you continued multiplying everything. So there's 10 numbers in this pattern. So we do 800, sorry, why did I say 800? 8,992 mod 10, which gives us 2. And so since we have a remainder of 2, we're going to look for the second number in our pattern. Sorry about that, which is 41. So we know that the last two digits of our number in the question is going to be 41 as well. And the question asks us for the sum of those numbers, so that would be 4 plus 1 equals 5. Find the sum of the values in the 18th row of Pascal's triangle if the top row is the 0th row. All right, did any of you get the answer for this problem? Jivitesh, if you said something, I think you were muted.
Oh yeah, I said I don't memorize like the 18th row, so I didn't do it.
All right, that's fine. Okay, so based on the lesson, there was an easy rule for this. So the sum of the values of the nth row of Pascal's triangle when the top row is the 0th row equals 2 raised to the power of n. You can see it there. So based off of that formula, what would be like our equation for the 18th row? N equals 18. So what would it be for the 18th row?
So we do 2 to the power of 18 to figure it out?
Yeah, that's exactly right. So we're looking for the sum of the values in the 18th row. So n here, the nth row basically just means like what number row. So we have the 18th row. And then if n equals 18, then we put that into our formula. So 2 raised to the n power. And 2 to the 18th equals this number. Okay, so on to today's content. So we're going to be first generalizing like a base n number system. But first we're going to go to the normal number system that you're probably familiar with, which is called the base 10 or the decimal number system, right? So as you guys know, there's going to be a ones place, a tens place, a hundreds place, thousands place, 10,000 place, and so on and so forth. And you should know how each of those place numbers correspond with like an exponent of 10. We're in base 10, so that makes sense. So it goes like from 10 to the 0th power all the way up, incrementing by 1 each time, okay? So this is going to be important later, so keep this in your mind. And now, what exactly does a place value mean? So you can see that there's a 3 in the ones place, an 8 in the tens place, and a 7 in the hundreds place. And you might remember from expanded form that means 700 plus 80 plus 3, because you multiplied the digit by its place value. So a 7 in the hundreds place equals 700. 8 in the tens place means 8 times 10, which is 80. And a 3 in the ones place means 3 times 1, which equals 3. But there are lots of other number bases besides just the base 10 or our decimal system. So what kind of place values do you think those would use?
Tens, thousands, hundreds, and then so on.
That's still kind of like the decimals thing. This is like it's going in the opposite direction, right? Those are getting really small because they're decimals. But that's a good answer. So anyway, we're going to generalize a base n number system where n is basically just representing another number. And so don't think of these places as like they have to be the tenths place or the hundredths place, because if you think about it in a more flexible way, it's going to help you convert to other number bases. So for example, the hundreds place in base 10 is also the 10 squared place. And n there just happens to represent 10 because that's the base we're currently dealing with. So here's the pattern. If you have a base n number system, the place values go from n to the 0th power on the right, and the exponent increases by 1 each time to n to the first, n to the second, n to the third. So say we're doing a base 3 number system. Well, this first place over here, n to the 0th, is going to be the ones place like always, because anything raised to the power of 0 is 1. But then the n to the first place, well, what place is that going to be? If n equals 3, what is this place? What is this place going to be?
Wouldn't it be a 10?
No, because remember, we're dealing with base 3 now. Pretend like base 10 doesn't
Then
exist. Sorry?
Then it would be a 3, right?
Yeah, because n equals 3, so n to the first place. This is the 3's place in base 3. And then n squared in base 3. What would n squared be?
9.
Yeah, exactly. And then 27, 81, 243. And then the same thing goes, like you just abandon everything, forget it. If you go to base 2, it just changes completely again.
Then wait, what would n0 be? Would it just be 0?
Anything raised to the 0th power is going to be 1, actually. So basically so this one is always going to be the ones place. That's the only one that's constant. In any base, that's going to be the ones place.
Okay, then.
So knowing this generalization, let's construct the base 2 number system, which is basically one of the most commonly used. It's also called binary, and you may have heard of it because it's the language that computers use. So to make the binary number system, basically n is just going to be replaced by 2 because that's what we're working with right now. And so say I put a 1 right here in the 2/3 place and we put zeros everywhere else. So take a guess at what this number, like 11000, is going to represent in binary in the chat. All right, I want everyone to put in their guess for what they think it is. And remember, multiplying the digit by its place value gives you like the value of the digit. And even if you have no idea, you can just put in like a random number if you want. Okay, I expect 4 answers. Okay, Aksha and Bharati, do you have a guess? Okay. So it looks like you guys did take random number to heart. But anyway, so going back to this base 2 number system. So what place value is this 1 in? It's in the 2/3 place, but what exactly is the place value once you convert that?
8.
Yeah, that would be the 8th place. So if we have a 1 in the 8th place, that's going to represent 8. It's going to represent a value of 8. Because like pretend like this is the hundreds place maybe. If you have a 1 in the hundreds place, that represents 100. basically because you multiply the digit by its place value. And then all of these zeros, there's a 0 in the 4th place, a 0 in the 2's place, a 0 in the 1's place. That's just not going to represent any values because 0 doesn't represent anything. So this number, 1000 in binary, just represents 8 because you only look at where there's a 1, and then you look at the place value of that 1, and then you multiply it to see what value it is.
So the rest of them don't really matter. So 0 is basically no number.
Yeah, 0 has no value. And it's also the same thing in base 10, right? 0 just doesn't have any value. So binary, the only digits used in binary are 1s and 0s. There's no 7s or 6s or 5s or like any other number in base 2, only 1s and 0s. And so let's see why this is the case. So say we're trying to represent the value 2 here. And in base 10, you would just write a 2 in the 1's place and be done. But you can't write a 2 in the 1's place in binary. So can anyone think of how we might represent 2 using just 1s and 0s? Like where would we put the 1? What place value would we put the 1 in?
The 2's 1, 1. The 1, 2 to the power of 1, and the rest would be zeros.
Yeah, exactly. So this is what it's going to look like.
10.
Yeah, so 10 in binary is 2, but it's sometimes easier to just refer to it like as 1, 0 to be a little bit less confusing. But yeah, you can also call it 10. So yeah, you're exactly right. So you put a 1 in the 2's place in binary, and so that's why we only have 1s and 0s, because everything just carries over if it gets bigger than a 1. So in every base, only digits less than that base can be used. So let me explain. In base 10, the only digits we're going to use are 0 through 9, because you can't just write a 10 in a single place value. That's too big and it's not going to fit. It overflows into the next place value over, because 10 ones equals 110. And so in base 9, only the digits from 1 to 8 would be used. In base 8, only the digits from 1 to 7. So in base 2, we're only going to use 0s and 1s. And so this pattern goes for any base. All right, so here's a question. What is the highest number you can count to using just your fingers? Like what's the highest number you could represent like this? If I asked you to count how many things are going to be on your fingers? 20? Interesting you say that. All right, so we would normally count like this, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And then we can also go on your toes if you want. But what if I told you that you can actually count up to 1023 using just your 10 fingers if you know binary? So let's watch someone count to 30. We're not going to watch them count all the way up to, oh God. We're not going to watch someone count all the way up to 1023, but we're going to watch him count up to 32 on just one hand.
Hello. Today, I'm going to teach you how to count up to 31 on one hand by using binary. Each finger is going to count as a binary switch. So here's all off, which is 0. Here's all on, which is 31. The way this works is if a switch is activated, you count the number on it, for example, 2, and you add up with all the other switches that are activated. And that number that you've added up, that is the number that's displayed. So for example, this is 3. 1, 2, 3. Or this is 4, 5. Yeah, 4 and 5 are kind of naughty. So let's go for 17. That's 16 and 1. And that's the way the system works. That's the way you read it. So let's count up from 0 to 31. Here is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. It's very simple, and as you get more and more practice using this system as opposed to 1, 2, 3, 4, 5, or 1, 2.
So isn't that cool? 31, counting to 31 on just one hand. And if you include your other hand, you can get up to 1023. Okay, so here are going to be the steps from converting. So a lot of the problems about number bases are going to ask you to convert from, say, base 10 into base 2. And so here are the steps for how you might do that. So example problem, convert 67 to base 2. So let's walk through this. So first, we need to remember the place values in binary. So that's going to be like 2 to the 0, to the first, to the second. And if we write them out, they're going to be 1, 2, 3, 4, 5, 6, 7. Oh, sorry, what am I saying? 1, 2, 4, 8, 16, 32, and so on. And now we're going to pick the place value that is closest to 67 without going over. And that would be 64. That's the closest to 67 without going over. And now we subtract 64 from 67 to get a remainder of 3. And we write a 1 in the 64th place, which you can see at the bottom. It's often really helpful to write out like lines on your paper to keep track of the place values. So we have a remainder of 3, and now we need to figure out how we need to find the next place value that fits our number. So 32, 16, and 8, and 4 and all are all too big because we only have a remainder of 3. So we put zeros in all of those places, but 2 does fit. So we subtract 2 from 3, and we get a remainder of 1, and then we write a 1 in the 2's place. So then we just repeat those steps until we reach 1. So we only have to do that one more time, and then we put a 1 in the 1's place. Okay. Does anyone have questions about this process?
Would you do the same for like a base 10? Would you do this? Like a 67 minus 60 for like a base 10 instead of a base 2?
Okay, well, you can convert from base 2 into base 10, and then we're going to go over that in the next slide.
Oh.
But I don't think it's exactly what you're describing, but kind of close. Okay, so converting from base 2 to base 10. Now, so that's going to be a number in binary. Remember, all binary numbers just have 1s and 0s. So we need to convert that to base 10. Now, step 1, again, same thing. We're going to remember the place values in binary, and we're going to look at only the place values with 1s in them because 0 has no value. So in this number, remember, writing out the place value does help. There's a 1 in the 32's place, a 1 in the 8's place, a 1 in the 4's place, and a 1 in the 1's place. And now we just multiply the digits by the place value. So the 1 in the 32's place equals 1 times 32. The 1 in the 8's place equals 1 times 8, or 8. 1 in the 4th place equals 1 times 4, or 1. Now, technically in binary, you don't have to multiply the digits by the place value because the only digits are just 1. But outside of that, you should. So then after you finish that, you just add up all the products. So for example, we just look at the place values with 1s in them, and then we add those up in binary. Oh wait, I think there might have been a mistake in the slides. Yeah, I don't think it equals 47 because there's not a 2. So maybe it should equal 45, but let's ignore that. Okay, so we're going to go to a review activity to practice converting from decimal to binary. And so here's a Jamboard, which I will post in the chat. Okay, so click that link and go on the Jamboard. Oh, interesting. Okay, so let me just get rid of everything first. Okay, so what we're going to do, everyone is going to pick their own page, and you should like put a text box or a sticky note with your name on that page. And we're gonna have 10 minutes where you should try converting these on your own. Okay, so just pick a random page and put your name there. I'm going to put my name on the first page because I'll use it to review the answers. And so just focus on the first column first because those are simpler. You can go to the second column if you want more of a challenge. Just put your name in the corner and pick a side. Okay, great. And I'll keep something up that might help you. I'll just keep this on the screen. It shows the place values, which might help you. Okay, so we're going to stop at 10:08 and just do your best. You can feel free to ask if you have any questions. Do you have a dash? I don't know if it's going to let you in if you don't use a Gmail.
Yeah, I know.
Okay. Well, you can just try doing it on a piece of paper if you want.
Okay.
Okay, so how are we doing? Is it very hard, very easy, or somewhere in between?
I'm not sure if my answers are right, but I'm just writing them on the paper, and then I'm gonna put them on the sheet on the thing at the last.
All right, that's
I'm
fine.
gonna finish the whole thing.
No worries.
I did 4 so far.
Okay, that's great. Okay, so I'll give you 1 more minute, and then I know these are probably somewhat challenging, so we'll go through and explain everything, and hopefully it'll make more sense. Okay, so go ahead and try and get all of your answers in. Okay, so let's go see. Okay, so converting 1 in decimal into binary. So let's first write out the place values. First step would be always remembering the place values in binary. They're going to be a little bit different. They're going to be just like the powers of 2. So 1, 2, 4, 8, 16, and so on. And remember that binary is composed of zeros and ones. So basically, if you put a 1 in the place value, that represents basically the place value, the value of the place value. And if you put a 0, then that means there's no value there. So for 1 in binary, you just put a 1 in the ones place. So it's just 1, same thing. Now, for 2 in binary, do any of you, what is 2 in binary? Everyone?
Is it 2?
No, because remember, we're only using zeros and ones. So basically, you have to put
Oh, so 1?
can you say that again?
So it'd be 2, 1, 21.
Not exactly. Okay, so let me get the text box. So let's see. If we're writing 2 in binary, hang on. 2 in binary is basically where you have a where you have a 1 in the 2's place. You just put a 1 in the 2's place and you put a 0 in the 1's place. Because what you're doing is you're multiplying the digit by its place value. So if you put a 1 in the 2's place, then that gets you 2. And if you put a 0 in the 1's place, that gets you 0. So 2 plus 0 equals.
So the binary form would be like 0, 1, 0, 0, 0.
Yeah, binary is only zeros and ones.
So, okay.
And
So the
so
next one would be 100.
100. 100, where's the 1? What place value is the 1 going to be in?
The 4.
Yeah, so 100 equals 4. But we're going to go to 3. So if we're going to 3, you have to put a 1 in the 2's place and a 1 in the 1's place. Does that make sense? Why?
Oh yeah, that we have to make it equal 3. Like 2 plus 1 is 3, and then for 10 it would be
Exactly.
8 and 2.
Yeah. So we're going to write 3. The value of 3 is like 2 ones, like that 1, 1. And then 4, like you said, is going to be 1, 0, 0, because you're putting a 1 in the 4th place and everything else is going to be a 0.
And then it would be 101 for 5.
Yeah, 101 for 5. Okay, so we'll just continue filling this out. 101 for 5. And
And
now,
then 7 would be 111.
that's right. Okay, so everyone besides Jivitesh, because I think he gets it, does this make sense? Like how you're supposed to basically try and find which numbers add up to the decimal number?
Yeah.
Okay. So now we're going to do 8, and 8 is kind of simple. So what would 8 be? Yeah, 8, you put a 1 in the 8's place and you put a 0 everywhere else, because all you're doing is having that 8 there. So 1, 0, 0, 0. Okay, so I think 9 and 10 are pretty simple, so we can go ahead and fill this in. So 10 is 1, 0, 1, 0, 9 is 1, 0, 0, 1. Okay, and now we're going to move to these harder ones over here. So 17 in decimal. We want to represent 17, and you can do it in the exact same way. It's just like a slightly bigger number. So we take these place values, and we have to figure out how to get 17. Yeah, so it's easiest if you start from like the biggest one. So the biggest place value that can fit into 17 is going to be this 16 right here. So we just go ahead and put a 1. And now we have 1 as our remainder, so we can't have anything in these. These are all going to be zeros. So we can have a 1 in the 1's place, like Jivitesh put in the chat. So that equals 17. 1, 0, 0, 0, 4. Okay, and then the next one is a little bit different, where you have to convert from binary into decimal. So basically, we're going to just write that binary number out onto here, onto our little place value chart. And then you need to multiply that by the place values to see what exactly it would equal. So Jivitesh says that equals 18. Do we agree? Yes or no? Let's get some consensus, okay? What does everyone else think? So we have a 1 in the 16's place and a 1 in the 2's place and 0 everywhere else. So do you guys think that equals 18? Yeah, 18 is correct here. Okay, so now we're going to do 25. And yeah, so 25, the largest value, 32 is too big. So you have to again go to 16. But now after we put in a 16, we still have 9 left over that we need to represent. So we can put it 1 here in the 8th place and a 1 in the 1's place. And these can just be zeros. So yeah, you're correct. Okay. So I think let's skip over like some of the ones in the middle, but let's just try these bigger numbers just as an example. So for the bigger numbers, you're gonna have to go to more place values. So I'm gonna have 128 and 256 right here. Okay. So just for a challenge, what would okay, so put in the chat, what is the largest place value that can fit into 200? Where would our first one be? Exactly, it would be in 128 because 256 is too big. And now we do 200 minus 128, which should equal 72. So next one, we can put a 1 here because 64 does fit into 72. And now we have 8 left over, so we put a 1 in the 8th place and 0 goes in everywhere else. Okay, so we can write that in 1 1 0 0 1 0 0 0. And now what is 256 in binary? Yeah, for 256, we just put a 1 in the 256 place, and we can put zeros everywhere else. Pretend like those are zeros. So yeah, you are absolutely correct. I'll just go type that in here. 1 0 0 0 0 0 0 0 0. Have to be careful how many you type. Okay, so let's go back to this. And let's see where we're at. So converting from base 2 to base 10. Okay, now we're going to have some practice questions. So express 43 in base 2. And remember, the rules are up there to kind of help you. And you might want to write out these place values on your own paper to make it easier. I'll give you 3 minutes to work it out. Okay, so 3 of you are saying the same answer, 1 0 1 0 1 1, and let's see. Okay, you guys are correct. So express 43 in base 2. That's our answer. And so we're going to break this down. So this 1 in the 32th place just represents 32. The 1 in the 8th place just represents 8. And the 1 in the 2's place just represents 2. The 1 in the 1's place just represents 1. So if we sum all of those together, we get 43. Oh, good job. Now express 241 in base 2. So these place values are written as exponents. So you might have to do a bit of converting on your own. And just think, what is the biggest place value that's going to fit? And go down from there. Okay, so this one was trickier, but you did get it right, Sanjay, so good job. That is the right answer, 111100001. So basically, so the largest place value that we're going to have here is 2 to the 7th, or 128. So a 1 in the 128th place. And then that leaves us with 113 left as our remainder. So this next place is the 64th place. So we can put a 1 there and subtract 64 from 113. So now we just have 49 left over. And this next place over is going to be a 32th place, which does fit. So we're going to put a 1 there and subtract 32 from 49. So now we have 17 left over. And this place is going to be the 16th place. So a 1 does fit in there. And now we just have 1 left over. So we have to put a 0 here because we can't fit another 8 in. But we put a 1 finally in the 1's place over there. And if you check your work, you can add up all the place values that have ones in them to see that that equals 241. Okay, so, oops, okay. I don't think you guys saw that long enough. But anyway, convert 110111 to base 2. And you can see that little 2 at the bottom is called a subscript. And that basically just means that number is in base 2. So you're going to see that kind of notation in more math problems. So yeah, just try converting this number to base 10. Yeah, it is 107. So good job. So a question asks us to convert. Okay, looks like a good amount of you got that. So 1101011 to base 10. And so basically what you should do is write up the place values and then put that number in those place values. And then you can simply just look at what place values have ones in them. So for example, 2 to the 6th place, that would be 64. So, okay. Oh, wait, sorry. Okay, that is a bit messed up, but it should say 64 for that first one, not 128, plus 32 because there's a 1 in the 2 to the 5th place, plus 8 because there's a 1 in the 2 to the 3rd place, plus 1 because there's a 2 in the 1st place, and then, plus 2 because there's a 2 in the 1st place, and then plus 1 because there's a 1 in the 2 to the 0th place. So when you find the sum of all of that, you get 107. Okay. question number 4, convert that to base 10. Okay, this one was easy. Well, you guys are correct. Okay. So yeah, basically just look at the place values and then sum them up. So 64, and there's 1 in the 16th place, 1 in the 4th place, 1 in the 2th place. And that's all. So sum this up, you get 86, like all of you guys are saying. Nice job. Okay, if that one was easy, here is a much more challenging one. So convert 1912 in base 10 to base 4. And remember, we did go over the base n number system. So this works for any number system. You just have to replace n with the number you're trying to go to. So in this case, replace n with 4. And then try to convert 1912 to base 4. All right, so this one is definitely challenging, but let's see if you guys can get it.
How do you do this problem? I don't remember.
All right, that's fine. So I'll give you guys a few more hints as to how you might do this. Okay, so we're trying to convert it to base 4, right? So, and then here's our generalization. Oops. Oh, dang it, I didn't mean to do that. Okay, well, whatever. Let's see. Okay, so here's the explanation for how to do it. So if we look back over here at our base n number system, you can see that the place values for any number base are just going to be like n raised to a bunch of different powers. So since we're trying to go to base 4 here, we basically just replace n with 4. And now we know what all the place values are. So 1, 4, 16, 64, 256, and 1024. And also, so we covered this previously. So every base, the digits used in that base are just like all the digits less than n. So base 2, we only use 1s and 0s. Base 4, we're going to use 0, 1s, 2s, and 3s. And then from there, it's kind of similar. So our number is 1912. So we're going to look at the biggest place value that's going to fit into, which is 1024. So we write, and only 1 is going to fit in there. You can't write a 2 here because that's more than the number we're trying to go for. So let me just write that over here to help. 1912. Okay, so after we take out 1024 from that, we're left with 888. So this next place value is the 256th place, and we can fit 3 of those into 888 because 3 times 256 is only 768. So we write a 3 there, but we can't fit 4 because that would be too big. And also you can't even write a 4 in base 4. So we write a 3 there, and then we subtract it from that, and so we're left with 120. Basically, we just repeat that process. So there's going to be 120 that, I'm sorry, 164 that can fit into 120. 120 minus 64 is 56. And then we ask ourselves how many 16s are going to fit in 56. Well, that's going to be 3 16s because that equals 48. And then 56 minus 48 is going to be 8. So then we put 2 in the 4's place because we can fit 2 8s. We can fit 2 4s into 8. And then we have nothing left. So we put zeros everywhere else. This is
Okay.
definitely complex.
I understand it now.
Yeah. So other bases where you don't just use ones and zeros, they're going to be considerably more complex. Okay, so, oh, hey, so they did pop up. I just didn't know they existed. All right, so time for our break. So 5 minutes, do whatever you need to do and return at 10:42. Resume. All right, so we've talked about base 10 and we've talked about base 2 or binary. But there's also one more base that's like pretty commonly used, and that's called hexadecimal, which is actually base 16. And now you might be thinking like, how can we even have base 16 if our highest number is 9? But we can definitely go higher because hexadecimal uses the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, and F. It incorporates the alphabet to go further. So A equals 10, B equals 11, C equals 12, D equals 13, E equals 14, and F equals 15. So you might want to write that down just to help you because we're going to be doing some converting. And so it's easy to mess up those. Okay, so since this is base 16, our place values are going to be the 1's place, the 16's place, the 256th place, and so on, 16 to the 3rd, 16 to the 4th, 16 to the 5th. So hexadecimal gets big like really fast. Even if there's only 2 digits, it's going to get up to a really big number. But so we're going to practice converting using this number. So remember, as always, what you should do is you should multiply the digit by its place value. So you can see here, we have a 2 in the 4096th place. So, okay, sorry, the explanation starts from the right, so we'll also start from the right. There's an 8 in the 1's place, so 8 times 1 equals 8. And then there's a D in the 16th place. So if you wrote it down, you should know that D equals 13. And so we multiply 13 times 16 to get 208. And then we have an A in the 256th place. So A equals 10. So that's 10 times 256, which is 2,560. And then finally, we have a 2 in the 16/3 place, or 4,096. So 2 times 4,096 equals 8,192. And now we just have to add everything up together. And our final answer, oh wait, oops. Okay, so let's find that final answer. So easiest to use a calculator for this, 208,250 plus. And our final answer for what 2AD8 equals in decimal is going to be 10,968. Sorry that it's not on the slides. So same principle. Hexadecimal just introduces a few more digits. And one common use of it is when you're coding colors. So like programmers, they'll commonly use hexadecimal to describe colors. And color codes will have 6 digits each. So the first 2 numbers represent how much red. The second 2 represent how much green, and the last 2 represent how much blue. So you may have seen this. It's written in the format like first you have a hashtag and then red, red, green, green, blue, blue. but then you substitute in the digits that are used in hexadecimal. So just having two place values in hexadecimal can represent the numbers from 0 to 255. So there's 256 shades of how many different colors there can be. And there's another way to write colors, which is like in a normal decimal format that looks like this. So basically, each of these numbers, like the first one is red, 255 is red, and the first two Fs also represent red because FF is going to equal 255 if you calculate it out. And so yeah, and then that describes white. You can see a couple more color codes up there, which are basically just so something important to remember is that it's like not all one hexadecimal number, but there's 3 hexadecimal numbers that are each 2 digits, and they just smash them together. Okay, so how did we get from that arch, the red, green, blue color code into that hexadecimal color code? Each of the decimal numbers corresponds to 2 letters in the hex code. So, and also, why does 255 equal FF? Well, so we have an F in the 16th place and an F in the ones place. And so from your notes, what does F equal? What number does F equal? Yeah, 15. Okay, so now we have to multiply each digit by its place value. So like you said in the chat, F equals 15. So we do 15 times 16, which is 240, and then we do the ones place. 15 times 1 is 15. So we add that together to get 255. So FF equals 255. Now, don't get too caught up in the color code aspect of this. This is just basically another way to practice converting between decimal and hexadecimal. And also, okay, so you can see here that white has the maximum amount of red, green, and blue, which might make sense to you if you learned in science class that white is just like a combination of all the colors. Okay, so we're going to do a bit of practice. So here is a color code written using its hex code. And so how would you write it using RGB? So just as an explanation, so 68 here is like equals is what you would write for R. So convert 68 is in hexadecimal, and then you need to convert it to a decimal number. And then 90 is another hexadecimal number, which you write into G. And then EC is the third hexadecimal number, which represents the number of blue. So that goes like in the B. But you don't have to worry about this format. So how about we just try converting 68 from hexadecimal to decimal. So 68 is in hexadecimal. What would that be in decimal? Okay, maybe this place value thing helps. So 68 is our hexadecimal number. Our first place value is 1, second place value is 16, and we define what, and we need to convert that into decimal. Okay, so is this conversion a little bit confusing? Okay, so I'm just gonna walk you guys through how to convert 68 from hexadecimal into decimal. So, okay, I'm not really sure what you mean by B. Like the options at the top, those are just telling you like what the digits represent in hexadecimal. They're not actually like answer choices. So, so we have 68 in hexadecimal right here, and then at the bottom you can see the place values. Oops, okay, so that's the answer to the question, by the way. So, so what we have to do is multiply the digit by its place value. So 6 times 16 equals 96. And then 8 times 1 equals 8. So you do 96 plus 8, which equals 104. And then the first two numbers in this hex code correspond to R in the RGB value. So that tells you it's 104. Same thing. So if you convert 90 from hexadecimal to decimal, you're going to get 144. And so let's go an example. Let's do an example with EC because that's like more special hexadecimally, you know. So EC, E is in the 16th place. Dang it. E is in the 16th place and C is in the ones place. So E represents 14, as you can see above. So 14 times 16, what does that equal? That would equal 224. And then C equals 12, as you can also see above. So this is in the ones place. So that just equals, that has a value of 12. And then if you add them together, you get 236. So that's why this number here is 236, because this number corresponds to this number. I think this color code stuff might be making this more confusing than it needs to be. So we can just like focus on just plain converting it for the rest of this lesson. So you can see like there's the full math. And after you finish, you should check to see if it makes sense. So this color, as you can see here, is kind of like a shade of blue. So it makes sense that our value for blue is going to be the highest, 236. Okay. Problem 1. Convert AB71 in hexadecimal into decimal. Okay, so try this out on your own. Remember the values at the top are just like the new digits in hexadecimal. And you just have to multiply place value by the digit it's in, then find the sum of everything. Okay. Is anyone like working on this problem, or are you guys like mostly just confused?
I got him.
I did
Do-
it. I think I did it like wrong because I got a huge number.
Okay, what number did you get? Because like hexadecimal does get really big really fast.
My number is like huge, not like big.
Oh, okay. Well, that's fine. Well, actually, Jivitesh is correct. The answer here is 43,889.
I don't know if I did the correct thing, but because A was 10, I did 4,096 times 10, and
Yeah.
then 256 times 11, and 16 times 7, and then 1 times 1. And then I added all the answers together.
No, that's exactly what you're supposed to do. That's perfect. So,
Oh,
okay.
I did the right thing, but then I accidentally multiplied one of the numbers with the other
Oh, I
one.
see. Well, yeah, that's probably why you got such a huge number then. Okay, so like Jivitesh explained, basically just multiply the digit by its place value. So you see all the digits up there, like the special digits that are letters. Those just correspond to like a number. So pretend like A is going to be 10, pretend like B is going to be 11. And then you see the hexadecimal place values at the bottom. So you just multiply the place value by the digit that's in that place value. And then if you find the sum of everything, it's going to get you that. So this is going to be like 40,960 and so on and so forth.
But what I did was I multiplied two of the big numbers instead of adding them, which resulted in like a huge number.
Yeah, make sure you add. Okay, so this one is a little bit different. You have to convert a decimal number, 1,839, into hexadecimal. So basically just look for the largest place and look for how many are going to fit into that place. So this one's definitely tricky, but I'll give you guys like 3 minutes and see how far you get. Jivitesh, you're really, really close. Just check your last digit. Yeah, that's the correct answer. 072F. Nice job. So this one's definitely
Yeah, I got confused if it was E or F. I wasn't sure.
yeah. Okay. That's perfectly fine. So first, we're gonna see like the highest place value that's gonna fit in our number. And so 4096 is too big, so I have to write a 0 there. But 256 does fit. And now our question is how many 256s will fit in 1839? So if we divide it out, we can see that 7 256s are going to fit because 256 times 7 is 1792.
Then
And
you
the-
have remainder 47.
Yeah, remainder 47. So we write a 7 right here because 7 of them fit. And then our remainder is 47. So a couple of 16s are going to fit in there. 2 16s are going to fit in 47. That gets us to 32. And our remainder is 15. Oh, wait, I think if I
And
click. Yeah. And then we have to write 15 once. But how are we going to do that? Well, that's going to be F. Oh, it pops up. Wonderful. Okay, problem 3. Convert the hexadecimal number D8 to binary. So to convert it to binary, what you can do is like convert hexadecimal into decimal and then convert decimal into binary. There's actually also another short trick to doing that, but we're going to go over that like after. So I think unless you guys know the special trick, just do it the long way where you convert it twice. That answer is very close, but not quite. You're missing one digit. One digit's off. Okay, so first step, what did you guys get when you converted this hexadecimal number and when you converted D8 into decimal?
13.8.
You got 13.8?
Yeah.
Okay, wait, you guys are just doing, okay, it looks like you guys are kind of like thinking of the trick already. Okay, so let's just go through. So one way to do this, like I said, is just convert D8 into decimal base 10 and then convert that base 10 number into binary. That's the long way, but kind of looks like you guys are kind of thinking about like the correct way, the shortcut way. So we're just going to go through like the long way first. There's a 13 in the 16th place because d equals 13. So we do 13 times 16, which gets us 208. And there's an 8 in the ones place, so that equals 8. And then for sum, that's 216. So 216 is this number in decimal. And then we can also just convert 216 into binary. Direct, like the slow way. But also, we don't even have to do decimal at all. We can just convert like d8 directly into binary. So d equals 13. And what is 13 in binary? That would be 1101. And then what is 8 in binary? 1000. And then you just squish them together to form the correct binary number. So I think you guys were like getting towards that. Yeah, so basically just remember hexadecimal numbers can just convert directly into binary. And then you just squish it together, each of the digits. You convert each of the digits and then squish them together. Okay, so I think we're gonna skip maybe the next couple of problems because I don't think these are very relevant. Okay, so here, Johnny wants to express his age in hexadecimal to feel younger. He is 35 years old in decimal, and help him figure out his age in hexadecimal. Oh, dang it. The answer is already on the screen. Okay, well, if he's writing 35 years old in decimal, 23 is how you would write it in hexadecimal. So you're asking yourself, so there's going to be like a 16th place and then a ones place. So how many 16s fit in 35? That would be 2. And then you have a remainder of 3. So if you put a 2 in the 16th place and a 3 in the ones place, that equals 35. Yeah. Okay, sorry about the answer already being up. But we're going to quickly look at how we can kind of do addition and subtraction in binary. So don't worry about joining the Jamboard, but I'm just going to show how it might work. So adding numbers in different bases is, you can do it like basically exactly how you do it in base 10. So, so first we have 1 plus 1 over here. And so you would write just like, you kind of think you might write 2 here, but you can't write 2 because we're still in binary. So what is 2 in binary? 2 in binary is 1, 0. And so we write the 0 here and we carry the 1 over here. And then we do 1 plus 1 plus 1. Well, that equals 3. But we can't write a 3 here because there's no such thing as a 3 in binary. So 3 in binary is written as 1, 1. So we write a 1 over here and then we carry this 1 up here. And then now we're back to 2. So we write a 0 down here and we carry the 1 over here. And then we have another 2, but we can't write that. So we get this 1, 0, 0, 1, 0. And now there's also a way to check our work. So if we convert this number into decimal, 1, 0, 1, 1, that would be 1 plus 2 plus 8, I believe. So 11. And then this right here would be 1 plus 2 plus 4. So that's 6. And then this number here is, okay, wait, maybe I messed up. Did I mess up? No, wait. This is 1, this is a 2, 4, 8, 16. So this would be 18. Okay, yeah, I messed up. This is not a 6, this is a 7. So now we're doing just 11 plus 7, and then we got 18. So that means this method definitely works. Check. See? Okay. Oh, there's still stuff up here. So now how does subtracting binary numbers work? Well, first, we're just going to pretend like we convert this into a decimal problem. So 1, 0, this is basically asking you for 2 minus 1. So our answer should be 1. But so remember, like normally when you're subtracting and there's not enough, we can't do 0 minus 1 here. That's not enough. So we have to borrow from our neighbor. And so this gets turned into a 0. And this becomes a 2, like a hidden 2, but it's not supposed to be a 2. and then we just do 2 minus 1 equals 1 like normal. Not the greatest example, but this is just to show you that that addition and subtraction basically just work the same way. Okay. And now, as a review of everything, we're going to do a Kahoot. So, it always comes up with the dumb ad like this. Okay, wonderful. We're going to play Kahoot. So go ahead and join with the pin. I'll put it in the chat. Okay, let's give it 1 more minute. If the other 2 of you would like to join, go ahead and do so now. Okay, we're going to start. Convert that binary number into base 10. Okay, correct answer here is 74. If you write out the place values, this is going to be 2, this is going to be in the 8th place, and this is in the 64th place. So if you find the sum of all of that, you get 74. Okay. All right, this one is going to be the correct answer because 144 is just like 128 right there. And this one is 16. And 128 plus 16 equals 144. All right, the answer to this is actually 5 ones. If you convert it out all the way 62 into binary, there's going to be 132, 116, 1 in the 8th place, 1 in the 4th place, 1 in the 2th place, and a 0 in the 1's place because it's even. So that's 5 ones. Yeah, so you guys all called this one. So nice job. If you just convert all of those, 32, 4, 2, 1 together, that equals 39. So good job. Okay, so this one you can actually convert it out all the way to solve it, but you can also kind of tell just by looking at it because this one has, so both of them have 1, 0, 1 as their first 3 digits, but this one has a 1 in that, I think that's the 8th place. Yeah, the 8th place, and this one does not have a 1 in the 8th place. That is 0, so you can already tell that this one's going to be larger. All right, so a hexadecimal problem. Yeah, so this one has the same principle. The first number is a B, and this number is an A, so B, the first digit matters more. It's like saying how 61 is greater than 16 if we're just talking about normal numbers. The first digit is the one that matters the most. So if that one's bigger than this one, then this one's going to be larger. Okay, this one you can also actually tell just from looking at it because it has a 1 in the 1's place and everything else has a 0 in the 1's place. So since like all of the other place values are even, if you add a 1 to it at the end, it's going to become odd. But if it has a 0 at the end, it's going to stay even. Okay, 2 of you got this one right. So if we convert it out, this is going to be like 3 plus 8 plus 16, 32, 64 plus 64. So this one is 75. And then let's see, what is this one? 1 plus 16 plus 64, I'm guessing. And so what is that? That is 81. So 81 plus 75 equals 156. Knocked out. Oh, skip the results. Sorry about that. Okay, we're going to skip this problem because it kind of takes a long time. Yeah, so you guys picked up on the last digit thing. Good job. Again, I'll correct. D equals 13. Yeah, she's incorrect here because base 7 will only use digits from 0 to 6. It can't use 7. And same thing for all bases. It uses like all the numbers less than the base. So base 10, it only uses 0 through 9. Well, here's an interesting one. Okay, so answer here is 52. So the possible values are going to be 1, 1, 0, 1, 1, and 1, 1, 0, 0, 1, because x can be a 0 or a 1. So if you convert those and then find the sum, it's going to be 52. All right, we'll do one more question. Okay. So if this is like the color one, we're gonna skip it though. Oh, okay, tricky. Okay, so you got it correct. Very nice. So 9C is going to equal 156 and A9 is going to equal 169. Remember, multiply digit by place value. But you guys know that, of course, because you got it right. Okay, oh, sorry, we're supposed to end this. Don't answer. Oh, wait, does it not give me an option to end the game? Okay. Now we can do it. Right, good job. Question mark, question mark, question mark. Good job, Sanjay. And good job, Kahoot. Okay, you were Kahoot. Leave page. Good job, guys. So that concludes day 4 of number theory. It's not exactly due tomorrow, but you do have homework if you want some more practice, and the answers will be just emailed to your parents, I believe. I'm guessing question mark was like Jivitesh. So yeah. So that's the end of number theory. Thank you guys for participating. And I hope you learned a lot. So if you have anything you would like to say, feel free to stay a while, but you're free to leave also. And remember, next week you have a new course, new topic.
Thank you.
Thank-
Bye.
Bye.